But there is another side to decreased energy use, deliberately reduced consumption through legislation or taxes. Does this play into the equation?
Yes, capping or forcefully reducing energy consumption will reduce people's income. Because there is a direct cause and effect relationship between energy consumption per capita and income per capita, reducing carbon emissions by 25% will reduce income per capita by 25%. Such a reduction can only occur painlessly if there's adequate replacement energy, up to 388 exajoules of fossil fuels in 2005. There's the target again. People need to understand the seriousness of this situation.
But as you've already said, this has a serious implication for the bulk of humanity living at the bottom of the income scale.
The peoples of the world now living in poverty must learn how to use more energy to break the bonds of poverty and participate in the world of today. The world must consume more energy, not less. 2 billion people around the world still do not have electricity. 50% of them live in Asia, 35% in India alone. In an era when the average European cow is subsidized by $250 per year, 1 billion people in developing countries try to survive on less than $200 per year. In developing nations such as Kenya and Nepal, 2.4 billion people still rely on traditional energy sources, wood and animal dung, for cooking and heating fuel. Everyone on all sides of the political spectrum is trying to improve the economic outlook for the people in these countries. By definition, this guarantees an increase in energy consumption per person.
What does income per person really mean to us? Income per person is represented by all of the goods and services we consume or have at our disposal. This is the wealth that fossil fuel energy has created for us. These are the things that give us control over our lives. They help us to live full and useful lives. They are clean water and air, safe and abundant food, good sanitation, pollution control, protection of the environment, healthcare, medicines, hospitals, doctors, nurses, houses, apartments, hotels, cottages, lawns, and parks, schools, malls, factories, heating, air conditioning, lighting, pets, toys, and fashion, communication, newspapers, TV, movies, cameras, computers, email, transportation, cars, trucks, trains, ships, airplanes, roads, bridges, canals, and airports. And the list goes on. Income per person is represented by all of the goods and services we consume. The average person in poor countries does not have access to most of the items on the previous list. The background of this slide is a picture of the world at night. It is clear that there is a tremendous amount of economic activity throughout Asia, particularly in Japan and South Korea. However, North Korea seems to disappear at night, highlighting its poverty and low standard of living. This begs the question, which items would you remove to cut energy use by 25%?
Exactly. This involves very difficult choices. Everyone's list will be different. We would all eliminate that which we do not have. Transportation, which consumes 1/5 of world energy, and electricity, which consumes about 2/5, are essential parts of everything in our lives.
How do you mean?
Everything in your home has come from somewhere. Every ballpoint pen, every bar of soap, every article of clothing. In fact, with the modernization of the economy through globalism, items often travel between countries during the manufacturing process. As soon as humans stopped being nomads, they moved everything in their lives around instead. Let's look at the specific example of food, which is something everyone can relate to. Consider where our food comes from. The average item in a supermarket has traveled 2,500 kilometers to get there. For every 1 calorie of carrot flown into Britain from South Africa, 66 calories of fuel were used to get it there. The processing and baking of breakfast cereal takes 4 calories of energy for every calorie of food delivered to the bowl. Manufacturing a 2-pound box of breakfast cereal burns the energy of about 2 liters of gasoline. 35 years ago, a club sandwich was considered exotic. No one in North America had heard of sushi, hummus, sun-dried tomatoes, pesto, or Starbucks. The modern palate has been developed, marketed, and delivered using energy. The items on the list we have just seen are examples of exactly what wealth, freedom, and a better life means for each of us. Every item is there because of fossil fuels. Reducing fossil fuel consumption will reduce the number of these items and their size. People and the environment will suffer in many ways unless adequate replacement energy is available.
Oil is very important to us. This slide shows the past discovery of oil in the 20th century. It is clear that the amount of fresh oil being discovered is decreasing dramatically. The more disturbing trend, however, is that since 1984, oil has been consumed faster than it is being found. The law of diminishing returns is also setting in. It takes more energy to extract oil from the ground, especially recovering bitumen from tar sands and converting it to oil. In the 1940s, it took the energy contained in 1 barrel of oil to find 100 barrels. Today, each barrel spent only gives back 10 barrels. If finding or extracting oil requires the equivalent of 1 barrel of oil as energy in for each barrel out, then normally the field is abandoned. If the input energy is not from oil, but from a source such as nuclear, in the future it may be possible to put in 3 units of nuclear power to get 1 unit of oil energy out, if the oil were valuable enough, such as for military use. We do this with electricity because it is so valuable to us. We put 3 units of fossil fuels or nuclear energy in for each unit of electricity we get back. This would not solve the oil supply problem, but would extend the time that oil is available, although probably at a much higher cost. The oil and gas reserves shown on this slide are from estimates made by the U.S. Department of Energy and converted to exajoules for comparison with information on the previous slides. The reserves in exajoules have been divided by consumption in 2005 to give an estimate of how long the reserves might last. This is not an accurate method for oil, but does give some idea of what might happen. We cannot take out oil at a constant high rate and have the flow suddenly stop. Production will hit a point where it no longer exceeds consumption. This is the peak we hear about. The peak will certainly occur before the 36 to 44 years shown here, even though smaller flows will continue for perhaps centuries. In summary, the life of oil is about 40 years. For natural gas, it is about 60 years. And for coal, it is over 200 years. This slide shows the U.S. Geological Survey's estimate of how much crude oil there is in the world. Consumed oil is oil we have already used to date. Proved reserves is the amount of oil which has been validated to be present in the world's oil fields. Undiscovered represents the amount of recoverable oil which might be found. Reserves growth refers to oil that might be obtained through more effective recovery procedures. The USGS estimates that there is a 50% probability that this amount of oil can be found and recovered in an economically viable way. The remaining oil is deemed unrecoverable. It will be impossible to recover all of the oil in the ground because it is in porous rock, something like being in a sponge made of rock, except rock cannot be squeezed like a sponge to recover the oil. It has been argued that this prediction is overly optimistic. For example, undiscovered oil and reserves growth are estimated by the USGS to be larger than all of the oil we have consumed to date. In other words, it assumes we are going to find and develop more oil in the next 30 years than we consumed during the last 100 years. There is an ongoing controversy about the true size of oil reserves. This estimate was prepared by Colin Campbell, a UK geologist, and Campbell-Laherrere. Both spent many years in oil exploration and other facets of the oil industry and have wide international experience. It is a more conservative and maybe a more realistic estimate. The point is that good information about oil reserves is not readily available because the owners of the oil are becoming more secretive as reserves diminish. The fact that oil companies are trying to exploit the more difficult sources of oil, such as drilling in the deep ocean and exploiting tar sands, is a good indication that oil is becoming much more difficult to find and to extract. There are two key points to consider when analyzing fossil fuel reserves. Firstly, reserves and estimates about how much of the oil can be recovered are independent of time. Secondly, however, consumption and production are time-related and are measured in barrels per day. When production per day cannot keep up with consumption per day, a production peak has been reached and shortages occur. Reserves and production rate are independent of each other. Production rate is the most important because it determines current supply. Reserves of various kinds may be enormous, but if oil cannot be produced from them fast enough, there is a critical supply problem. Oil is not like other minerals, such as uranium, where the volume of reserves increases as the price goes up because lower concentrations of the mineral become economical to mine. The nature of an oil field is such that total volume is fixed. The rate at which oil can be recovered diminishes as more and more is removed. The effect of increasing oil prices is to lengthen the time that oil can be recovered, but at smaller production rates every day. Unconventional oil cannot be extracted fast enough to meet demand. Most unconventional oil production is an industrial mining operation where the ore is removed from the ground and processed into synthetic crude oil. The facilities and raw materials, such as water and natural gas for heat and hydrogen, are huge compared to drilling a hole and pumping out crude oil ready for the refinery. As potential for finding new oil deposits shrinks, 4 sources of unconventional oil that become attractive. The tar sands of Alberta are the easiest to exploit and have potential to produce 300 billion barrels of synthetic crude oil. In the 8 years from 1997 to 2004, $34 billion was invested and production increased from 0.18 to 0.36 billion barrels per year. Plans are in the works to invest about $70 billion in the years 2005 to 2015 and increase production from 0.36 to 0.9 billion barrels per year. This is a drop in the bucket compared to current consumption of 31 billion barrels per year. The simple fact is that tar cannot be recovered and converted fast enough for the Canadian tar sands to be more than a small contributor to world oil supply.